So we have just seen that not all the layers are equally important, that many of the neurons the weights of those connections can be set to zero. So that brings us to an interesting idea that has been called the lottery ticket hypothesis. So the lottery ticket hypothesis is that when you have a complex network with a lot of weights, then initially you have many possible connections from the input to the output, and all of them are random. But just by this randomness, some of these connections somehow bring some useful information from the input to the output. And then as the network is learning, what happens is that those connections that were useful from the very beginning, they become somehow reinforced so that the information is actually flowing correctly from input from the beginning to the end, and the rest of the connections just somehow fluctuate or go to zero or whatever because they are not useful. So this is this lottery ticket. So all the neurons in all these layers somehow they buy a lottery ticket, and just randomly some of them are winners, and these winner tickets are the ones that are preserved and reinforced during the learning. And that is why you can remove some of the connections, so remove these synapses, or even remove some of the neurons because they're not contributing to the final result. So the pruning and somehow regularization, this especially this L1, where it is very obvious that we are setting to zero some of the coefficients, then it is related to this lottery ticket hypothesis. And here we have a blog or an article that discusses this idea. And it has been shown experimentally. So at the beginning, when you compute what is the correlation between the activation in layer 1 and layer 2 of the different neurons, so there is a correlation matrix, and at the beginning it is just random and almost no correlation. But at some point, as you train, you recognize that the activations in layer 1 somehow are correlated to the activations of layer 2, but in groups. So these groups correlation, if you set everything to zero, what is happening is a kind of routing. So the information from layer 1 is routed to neurons in layer 2. So a group of neurons in layer 1 is sending their information to a set of neurons in layer 2, and this set to this set, this set to this set. So you have routes of information in these neural networks, and these routes are established at random, in the sense that at the beginning you had random initialization. You don't know where the routes will form. So there are different ways of pruning. One of them is simply based on the magnitude. So you take the small weights in absolute values and you set them to zero because they contribute less to the output. Another way to prune is by looking at the gradients. So as you have been training, you have these accumulated gradients that were a part of the moment, and these Adams and Adagrat and so on optimizers. So you have the accumulated gradient. So the accumulated gradient tells you how much sensitive is the cost to changes in that weight. If it is not too sensitive, so the accumulated gradient is one of the smallest, that means that that neuron is not, that weight is not important. And there are more sophisticated ways to prune. One is this information based, in which you use some matrix like the Hessian to assess the Hessian is a kind of second order derivative, so the gradient is first derivative, Hessian would be second derivative. So you can measure what is the importance of that parameter, and here you have more articles related to the study of these effects more in depth. There is another interesting idea, that is to integrate the sparseness during the training. So this is an idea that was published in Nature, and the idea is to, for instance, let's say that you are training at some point and you have some weights, and then what you do is that you take the ones that are closest to zero and you remove them, so you no longer they can be updated, no longer they don't exist anymore. And if you have removed 3 weights, you add new 3 more you add 3 more weights at random between the 2 layers. So let's say that you have removed 3, and then from this network to this network you add 3 more connections, and then you at random, and you initialize at random, and then you keep training. So from epoch to epoch you change all these weights, so that, and then weight structure, so that in the long run you will have a sparsely connected network with only the useful connections surviving. So this is a summary of all these ideas. And so we have seen this lottery ticket hypothesis, regularization, different ways of pruning, and even this one we have not seen, but for instance the weight matrix, this W, it is a matrix, so you can approximate this matrix by a low rank approximation, and then factorization, and then this low rank factorization will remove the unimportant weights. So there are many dropouts is also another way to regularize, and then here it is a summary of what it is doing, the different pros, the different cons, and then you may decide where to go. So some of them are applied during training, some of them are applied after training. I forgot to say here that, for instance, here, once you prune, you may fine-tune your network, so retrain your network starting now from these zeros, so that maybe one of the weights now decide to change again to 0.3, and this process can be reiterated. So now again you remove the small weights until you have something that is has a lot of zeros. Some of them, some of the pruning, they have some advantages over others. So for instance, let's say that you keep the fully connected networks with many zeros. When doing inference, still you will have to do those multiplications, even if you are multiplying by 0, you will have to multiply, so there is no saving in terms of inference time. If you remove the connections, or you remove neurons, then it is much more GPU efficient, or you remove layers, they will be much more GPU efficient, because those operations you will not need to do. So this is all for these ideas of sparsity and removing networks, removing layers, connections, neurons, and how they are related to regularization, to this lottery ticket hypothesis. And see you in the next video.